Got it. Sorry about that. So again, one way that we can reduce the amount of energy that homes use or buildings use is to, again, for people to live with temperatures a little bit cooler in the wintertime, a little bit warmer in the summertime. The other we can do is, I put a picture up of this Nest thermostat that you can have talk to your smartphone, so you can have that set up so when no one is home, you can set the temperature back or set the temperature up right now. So if you're sleeping in the evening, you can make the house a little bit cooler. If you leave your house going to work, you can set the temperature to be a little cooler as well, right? These are tools that have existed for many years, but now they're more sophisticated with things like the Nest thermostat and your smartphone, right? You can dial up the temperature in your house. Hey, your restroom or leaving the office, you're going to be home in half an hour or 45 minutes. You can dial up your Nest thermostat on your phone and turn the temperature up so the house is a little bit warmer when you get home. Right? What's the other side of temperature differential? Temperature difference, right? That has to do with the outside conditions. This is typically at design. So again, engineers or people that design this stuff will pick out the design conditions, right? What is the textbook value for how warm or how cold it is in a particular area, right? So this is kind of a given based on the climate or location you're designing in. Right? The other piece of the equation here is the U factor or the R value, right? They're the inverse of each other. Right? U and R are properties of the material or the construction. Picture here's the R value stamped on a piece of insulation, or the U factor that happens to be a sticker on window. So again, the other way that we can reduce heat loss and heat gain is by our choice of materials, right? Using more insulation, better windows, right? Lower U value, higher R value, right? We're Americans who always have to think of whether bigger is better. I think as Chris said, we kind of fell into that trap in terms of our houses, right? We thought that, a bigger house is better, and shows that isn't necessarily the case. But in terms of insulating your walls, where you're looking at R value, yes, bigger R value is better, right? The more insulation we have, the better off we are. When we're looking at, so wall insulation is typically rated in R values. Things like windows and doors are generally rated in U. So U is the inverse of R, so we want U to be a smaller number. In the case of a U value, smaller is better. We haven't really talked about it in this class. I'm not sure we'll get around to it, but we have building codes that specify minimum requirements for insulation and windows in various components. We have what are called the I codes, right? A family of codes. IECC is the International Energy Conservation Code. So that would lay out minimum requirements for how much you have to insulate depending on the location. And in the code books, they all tend to have a map that looks something like this, where they've broken the United States up into different climate zones. A little hard to see on the map, but it's basically by county. So the code requirements for for U values and R values vary by climate zone, right? That makes sense. The things that we do in hot and humid Miami Beach are going to be different than what we do in Duluth, Minnesota, right? Those are two entirely different climates. So the code recognizes that and points us in different directions in terms of how much insulation is required. This is a little hard to see on the slides here. Sorry, I'll post these on Blackboard, but the code will typically have a table like this that will provide the minimum values for insulation, right? So we in Chicago are in climate zone number 5. So this is the brand spanking new. This is 2021 IECC, right? So this is saying to meet the building code minimums for insulation, we either have to have 20 plus 5 or 13 plus 10. What that means is if we're doing a stud wall, we either have to now do a 2x6 stud wall with R20 insulation and R5 of continuous insulated sheathing on the outside, or if we're going to do a 2x4 stud wall that gets R13 insulation, we need roughly 2 inches of insulated sheathing, right? That's the minimum. So again, the building codes are slowly but surely requiring higher levels of insulation, helping us drive down energy consumption and carbon consumption, right? Those are all good things that we need to be doing. The IECC, the building code requirements, will also have stipulations related to air leakage, right? Air leakage or infiltration. Right. I think earlier on we talked about building rating systems. We need to distinguish between a building code, which is a mandatory, it's something that we must do, and a building rating system or a standard, which are optional, right? Those are things we can do. I mean, ideally, in the work that we do here, we're going to do better than what the minimum code requirement is, right? If we're gonna hit to some of these things, right? If we're gonna get to net zero buildings, we have to be doing a lot better than building code minimums. In all these rating systems like LEED, right? LEED has the concept of a baseline. We'll see it a little bit more when we talk about LEED strategies for EA or energy and atmosphere, right? Baseline typically means how much energy or how much resources the building would consume if it was constructed to meet the requirements of the building code. And then in a rating system like LEED, we're trying to do better than the building code. We're going to score points by performing better than the building code, right? The whole idea of a rating system like LEED and some of the other rating systems is to encourage us, is to set the bar higher and to encourage us to improve the performance of our buildings, right? We've talked about this, that we need to do better. If we're going to get to building net zero buildings by 2030, right? We have to raise the bar. We have to build better buildings, right? More insulation. So I show this graphic here of this young woman looking up at the bar, right? That's us in the construction industry. We have to set our sights higher and figure out ways to build better buildings. Just some definitions here, right? Thermal boundary, this is all the places that separate the inside from the outside, right? So these are all the parts of the building where we need to be concerned with insulation, right? The insulation details may vary depending on where we are, whether it's a wall or a ceiling or the basement wall or the floor slab, right? All these things will get different details as we'll see, but these are all areas that we need to concern ourselves with if we want to drive toward that higher performance, right? If we want to raise the bar and drive towards higher performance, right? Just another picture of the same idea, making sure we wrap that insulation and the air barrier around all those surfaces that form the thermal boundary, right? The boundary between inside and outside. Right, when we look at this is a picture of a house using what's called thermography. So in this case, the colors come up differently depending on whether there's more or less heat loss. But this picture gives us an indication of what's called thermal bridging. Thermal bridging means that the stud walls in the building, you know, that heat actually bypasses the insulation because it's going right through that solid stud. So that's part of the reason when we looked at that table a minute ago about the 20 plus 5 or 13 plus 10, that second number is the continuous insulation that's meant to try to address this thermal bridging, right? So if we're to meet the current energy codes, if we're building a 2x4 structure with our 13 insulation, we need our 10 continuous insulated sheathing, right? That's roughly 2 inches of insulated sheathing on the outside of our stud wall to help address thermal bridging. So let's look at some types of insulation. I said, do you remember this from, hopefully you guys are learning about some of this stuff if you're taking ARC 108 at the same time as my 110 class. We're trying our best to coordinate presentations in the two classes here. But yeah, blankets and bad insulation typically come in standard sizes. We're putting them between the studs or the framing members. They can be unfaced, right? As you see in the picture here, that pink is kind of the fiberglass insulation, or that insulation can be faced with either craft paper, which is kind of a brown paper, or foil. You know, the facing provides some additional thermal performance. But again, these blankets and bats are really meant to be installed between standard size framing members. And again, here's our values are 13 would be in a 2x4 wall, our 19 in a 2x6 stud wall, our 30 generally would be insulation in a roof or a ceiling. Again, with R value, bigger is better. So higher R value means we're providing more insulation. Right, same thing here. Table of blankets and bats, typically going to see in attics and ceilings and exposed walls. I'm hoping I'm still coming through here. My computer's telling me I'm losing some connection here. So we're also going to look at rigid foam board. So where are some of the places that we would see rigid foam board? We're going to see it in the exterior sheathing, right? We just talked about 20 plus 5 or 13 plus 10, right? That would be a rigid sheathing on the outside of the wall. Excuse me. Almost ready for break here. We're going to see that on the exterior foundation walls for the basement, underneath the floor slab, and also potentially in a commercial roof. Sorry, folks. Again, some typical types of rigid insulation, expanded polystyrene, extruded polystyrene, or polyisocyanurate. Again, these are all going to have different material properties. Again, you as the designer or the contractor will have to, pick out the material that has the properties that meets the requirements of your particular project. Probably the important one would be if insulation is going below grade, right, under a floor slab or on the exterior basement walls. We have to make sure that that material is going to stand up to that it has the compressive strength to stand up to the forces that's going to take, and is going to retain its characteristics, when it's exposed to a wet environment. Let's do this. Let's take a 10-minute break here or so. Give me a chance to refill my water glass and get my voice back. So we will pick up here at the top of the hour.